Okay, let's start. Good evening. Welcome back. Can you take a seat? So let me remind you what we are doing. And I have a good news. Today's lecture is slightly simpler. This is good news. Slightly. Epsilon simpler, yes. But epsilon can be big. Okay, so I remind you what we have seen last week. M is a smooth manifold of dimension M, and I have defined these set which are functions on M with value in the set of R tensor. So it means at every point, it's called the exterior differential form or just a R form. It's a function on M, and at any P, you associate a tensor, which is a multilinear map on R copies of the tangent space. And if you do the sum of these space from R from 0 to M, you get what is called the exterior algebra. So think about this as it's not a real sum in the sense you do not sum the different ingredients. You just put them next to each other. But if it is an algebra, it means that you can do addition, and you do the addition pointwise. So at every point of the manifold, you pick a point, and then you have tensors, and you can add these tensors. And the multiplication is with a Vetch product, also pointwise. The good point is we have a basis for these spaces whenever we have a chart. So remember, a chart is a local map from the manifold to Rn. And I have defined this kind of objects. Today, we will use them when we define integrals, and it should become simpler. You can think about this as kind of, it's not true, but it's a kind of infinitesimal going in some directions, and they will be used for defining integrals. So these are bases when you take R element between 1 and M, and you take all of them, you generate a basis of this space. Okay. And then probably the most complicated object is this D, which is called the exterior derivative. It's a function, or it's a map from this exterior algebra to itself, and it has different properties. If you take an element of degree 0, so the first one in this sum, and you apply this D, you get what was introduced a week before, the differential of F. And I will not recall now, but we gave a definition to this, and it means that this, on the first degree, this D is exactly the differential. Then it has a formula for any product of two tensor field. I didn't recall it, but we have seen a formula. And the very important point is if you apply it 2 times, you have 0. In fact, this will become clearer today when we have a generalization of Green's theorem, Stokes' theorem, and divergence theorem. We will see this. I emphasize D is local, so it means if the tensor field is localized on a small subset, then the D is also a function on the small subset. And there is an explicit formula. We will soon have a report about this, which shows how we can get it once we have a chart. Then I introduce orientable manifold. So it's a manifold with a maximal atlas. We have seen this a long time ago. So that when you compute these transition maps for different alpha and beta, this is a function from Rm to Rm, or part of Rm to part of Rm. You can compute the Jacobian, and the Jacobian has to be positive. Then we call this manifold orientable. And there is a statement which says that this is equivalent to having a form of degree M, so the dimension of the manifold, which never vanish. And I would be very happy if somebody makes a report, I indicated in the notes a few pages, where it is explained why these two notions are related. Then we introduce manifolds with boundary, smooth manifold with boundary, because at the beginning of this course, we mentioned topological manifold with boundary. Now, when you have a boundary, you need to say what is the derivative. And like Hevidu said last week, I'm cheating in the sense that if I want to define a function on a set with a boundary, what we do, in fact, we put this in a bigger set, and we assume that the function can be slightly extended on this open subset. This is the way we do, and this is the way we have enough freedom for constructing the theory. It turns out that if the manifold M is orientable, its boundary, and I gave a definition for the boundary, is also orientable. We will use it in Stokes' theorem. And the last thing I introduce at the end is that if we have what is the notion of partition of unity. So first here I introduce the notion of locally finite cover. And a counterexample is a cover of this type, where the central point will have an infinite number, or will be contained in an infinite number of sets. So I introduce the notion of locally finite cover. And the smooth partition of unity is a collection of smooth functions, all positive. They satisfy that they do not intersect in an infinite number of time. So it means every point is only contained in a finite number of the support of this function, the place where they are not zero, and this sum up to 1. And this sum is well defined because at every p, precisely, we have only a finite number of these sets. So this is all what we have seen last time. And I don't remember if I wrote the title of this new chapter last time. Did I write? Okay. But let me just write again the title. So this chapter is about integration. It's integration on manifolds. This is chapter 4. Integration on manifolds. And the section 4.1 is integration of M forms. M forms. And you should easily realize that it's not so easy to define an integral on a manifold, because when we deal with Rn, we have the Lebesgue measure we are familiar with. We take an interval, we subdivide it, and so on. This is quite natural. Or in 2 dimensions, you also have this decomposition on these Riemann sums. But when you're on a manifold, it's not clear what would be a small element of volume. So we need to do something. Okay. So the first thing we integrate are precisely M forms. So we consider a manifold M, a smooth manifold. I will consider it today, it's, at least in this chapter, it's oriented. It means, what is the meaning? It is orientable, which I have defined. And I remind you that when it's orientable, you have 2 orientations. So you choose one. Choose one of them. Choose one. So when we say oriented, it means it's orientable, and we have chosen one orientation. And let U alpha phi alpha be a maximal atlas. Preserving the orientation, yeah. Because we may have some atlas which do not preserve the orientation, but we say it's orientable when there is one which has a certain property, so we choose this one. Maximal atlas preserving the orientation. Okay. And of course, the dimension of M is small m. I'm using this convention. That's why I speak about M forms. In some books, they would speak about N forms simply because the dimension, they choose to call it N. So now I choose a M form. So M. So remember, it's a function defined on M with value in the set of M tensor. And I will assume, okay, let me do the picture of the manifold. You know, we have local charts. This is a U alpha, or let's call it U beta, and this is a phi beta. But we have this for, this is a phi gamma and U gamma. Okay, we have the covering like this because we have an atlas. I'm going to assume, I don't know now how to integrate if the function phi is defined everywhere. So I will assume for at least the beginning that phi is only defined on this and is 0 everywhere else. So I assume that the support of phi, remember the support is where it is not 0. So I assume that it's, so this support is inside a certain U beta. Just one, or fixed beta. Or fixed beta. So it means, of course, this is, I'm cheating because I just represent a function, but I'm supposing that the function does something on U beta and elsewhere it's 0. Of course, it's not such a function because we are dealing with a M tensor. But the support is in U beta. And I will also assume, you should not worry about this. Assume that the support of phi is compact. Why do I need this? Simply because some of these sets can be very big. And we know if we integrate something on Rn, for example, it could diverge, while if we integrate on a small set, it's always finite. So I assume that the support is not too big. And it doesn't follow from the previous assumption because this UB could be quite big. Okay, then what we know that this phi has a local representation. In Ole, this is exactly what you have done in your report. It means that this phi can be written as, this phi at a point P can be written as a function AP times dx1 P times dx M. For what is it? I just decomposed on a certain basis for a smooth function on, in fact, on U beta, a support on U beta. So what does it mean? This is a basis, this is a basis of this TP of, no, I should write of that this M of TPM. And why we have, I'm saying it's a basis while it's only one vector, it's because this space is one-dimensional. So remember, for M equal to the dimension of the manifold, this space, this set of tensor is one-dimensional, so I have everything with just one of them. Okay. So we have such local formula. Okay. Now, remember this phi beta is going to, from U beta to a certain image phi beta U beta, which is a subset on Rm. This set here is the image of U beta. So this is phi beta of U beta, and it's a bijection between these two sets. Okay, so I can define the inverse phi beta minus 1, which is going from this range to U beta, because it's bijective. And in fact, it is a diffeomorphism. This is how we have chosen diffeomorph. So you have also differentiability. It's a smooth map. It's a diffeomorphism. And okay, it's a little bit complicated, just this line, but then it becomes much simpler. I just want to be precise enough. When you have a diffeomorphism from one manifold to another one, we have seen that the star or the pullback is transform a tensor field of this one into a tensor field of this one. That's just a way to have something, because we are going to have a tensor field on u beta. This is our phi. What I'm saying is that we have a natural way, and we define it, to bring it from a function on this set to a function on this, and you are more happy because this is on Rn. And in fact, we even have a very simple formula. What is the image of phi by this pullback? Then the image of, so it's phi beta minus 1 star applied to phi. It's simply A times dx1 dxm, which leaves, this is an expression on R, or basis of the same thing, lambda m of Rm. Okay, and now if you don't really need to know this because the next definition is very simple. Nevertheless, it makes the theory consistent. And we will see in a second. So now what is this? Oh, I should have. Yes. Yes, but we identify it with Rm itself. You're right, but yeah. Definition, what is the integral of this M form? So for M oriented, as I have taken, and phi inside this lambda m of m, no, of u beta. I take it with support in u beta, so I can just write this. Then the integral of phi on m is the integral of phi on u beta, because everything else is not interesting. It's 0. But let me give you the definition now. This is the integral on phi beta u beta of maybe this is the simplest formula I've written so far, because this is just an integral on Rm. This is, look, we have a function. So let's check this. Oh, I should do the picture again. We had u beta, phi going to part of Rm. This is part of Rm. So let's check. We integrate on this, which is the image of u beta. So it's part of Rm. And this function is indeed defined here. You go back here. And then A was a function defined on the manifold. So this, when you evaluate, this is just a real number. When you evaluate at a point, it's a real number, and you integrate. So it means you have a function defined here, and you integrate on this. So this is a definition of the integral of M tensor field defined only on a small set here. Yes?
The order of dx1 to dxn, does it matter?
No, in calculus 2, it doesn't matter if, no, this is, and you know, this is just a notation. This is just a notation for a limit of Riemann sums. And this doesn't matter. In some places, they would maybe put M integrals here. I put just one. Okay. So we have a definition. And of course, now everything should become more consistent because, as I said, this is just a notation. And this is just to remind you a small volume. And it was already encoded in this notation. So this, of course, it has a deeper meaning, but yeah, we can integrate M forms on a subset of dimension M. Okay. Of course, we would like to have some properties for this definition. For example, if there is another U alpha here, and if the function phi, which I again represent like this, is in the intersection, it means I could have chosen this chart, or I could have chosen another one with a phi alpha on another part of Rn. And of course, I would be unhappy if I don't get the same answer. And of course, this doesn't happen. It's an exercise. If phi, if the support of phi is inside an intersection, is inside U beta intersection U alpha, like on this picture, then of course the integral of phi on U alpha is equal to the integral of phi on U beta. And the one on U beta is with this phi minus 1 beta. The one on phi alpha is with alpha. So it means it doesn't depend on the choice of the chart. So it means the integral is independent of the chart. Of course, you have to understand it correctly. If you take now a chart here and phi is supported there, it's just meaningless. But if it is in the intersection, it does not depend on this. Do you have any question?
There can be the non-equivalent maximal the maximal charts, right?
Yes, you may have different atlas, but I fixed one from the very beginning. No. This is a different problem. If we will come back to it maybe later, but yeah, I fix an atlas, so everything is fixed from the beginning. If you change this atlas, of course, you may change this integral. Yes?
I have a question about this definition of integral.
Yes.
We're using dx1 to dxm, but this d, they're defined for real numbers. How are they like, this d, this is the integral on R, on Rn.
But
right?
this is an integral on Rn.
So how does this d relate to the d's we have? Like this is a definition in the course of differential geometry. So we would love to know how it's connected to the d we have defined, to our differential.
I told you, this is just, I define all these objects, but now it's a way also to remember that this is it can be integrated on something of dimension m. It's a way, these things are also a way to organize your computations. And I give a definition, M form can be integrated on a subset of Rm, so of dimension m. No, because this is really just it's an integral.
So that's F1 with the integral symbol, and this is just like.
Yeah, this is just an integral of a function with value in R. I mean, I told you this is a simple definition. Now, you would like to have something slightly more general, because if your phi is not located on just one, but it has a support which is on different charts, then you would like to have a definition of an integral of such a form. Or if the form is defined everywhere, you want to generalize this. And this is where we are going to use the partition of unity. Okay, I keep this for the definition. So now I will not record the partition of unity because I introduced it last time, but for general phi M form, we need a partition of unity, which I have introduced. I need to say just a little bit more, because let me draw again the manifold. I need a compatibility condition, which I'm going to introduce. Why? Because let's take a manifold. Okay, we have our maximal atlas, which give us some u beta or u alpha. I would like to have a partition of unity. Remember, these are functions which sum up to 1. I would like to have them compatible with this structure. So I would like to have them be inside. The support of this partition of unity should be inside the set given by the maximal atlas. So let me now just mention this. I just take F beta, a partition of unity. And I take a family, the alpha, a cover of a partition of unity on M and a cover of M. So we have two ingredients. I have first a cover, so a family of sets. I'm not even asking that they're open for now. A family of sets and a family of functions. They are a priori independent, but the family F beta is subordinated to the family V alpha. This is subordinated to V alpha if for any beta for any here, there exists V alpha, I call it V alpha, with the support of F beta inside U alpha, inside V alpha. So it means whenever we have one function like this, the place where it's non-zero is contained in one of them. And this is quite natural because we have defined something in terms of 1 u beta. So now if I add a partition of unity somewhere, I will have to stick to this notation. We will see in a second. So the notion of subordinated, you have a covering of your space, a family of functions summing up to 1. You want the place where each of them is non-zero to be in one element of your cover. You can wonder, does it exist? And of course, it exists. Theorem for any cover of M. I need to say a little bit more because if I just say cover, it could be very nasty sets. For example, if you think about the real line, you could take Q and R minus Q. This would be a cover, but of course you would have a problem. So for any cover of M by open set, by open subset, notion of open is very important. By open subset, there exists a partition of unity. Subordinated to it. Subordinated to it. So it means take a cover by open set. You can construct and even explicitly a partition of unity so that each function has a support in one of them. And now you can guess what I'm going to do. This is typical in physics. You add an identity and you decompose this identity. On the Hilbert space, it would be on a basis. Here, it's on a partition of unity. So now I can call it as a new definition for any phi in this set of M forms. We set the integral on M of phi is the same as the integral on M of 1 phi. I just add the number 1. It's the same as this one is a sum of F beta phi. This no, integral. And because it's sum up to 1. And now you see why I wanted this to be subordinate, because for each F beta, I have a U alpha. So this is a sum on beta of integral U alpha F beta phi for the corresponding set U alpha.
Have to be countable.
The cover has not, this is a good point. The cover, I did not assume that it is countable, but in the notion of partition of unity, there is a locally finite. So it means if you take a cover which is nasty, okay, too many sets, not countable, still you can, it's a manifold, it has locally the structure of Rn, so you can still extract a partition of unity which is locally finite.
Okay.
No, if it is locally finite, we can do it. But please don't think always about the most complicated situation. Do a nice picture, be peaceful. And okay. Of course, you can always make things more complicated, but so now we have a definition for an integral of an arbitrary M form. There is still one point. Maybe you observe I didn't make one assumption. I need to be, I didn't assume that the support is compact. So it means some of these support could be very big, extended. So this is meaningful if only it converges, this integral converge absolutely. So I should write a remark. So if you don't have any, if you don't want to have any problem, you take phi of compact support. So remark. If the support of phi is compact, there is no problem for the integral, no problem for the integrals. Otherwise, so if it has not a compact support, otherwise, we assume that the integrals are absolutely convergent. So it means they converge when you take an absolute value, which is quite standard. So just be a bit careful. If you are on a compact manifold, there is no problem if phi has a compact support. There is no problem if the manifold is not compact, if you have some sets which are not compact, just be aware that you have to check that it's convergent. So far, so good, because this definition is rather simple. We did it on a small piece, and now we put the pieces together with a partition of unity. You should complain, heavy do. You didn't complain about the most important thing. Does it depend on the partition of unity? Remark, of course not. This integral does not depend on the partition of unity. Otherwise, it would be very annoying. And it's not completely trivial, because if you want to prove it, you need to do with two partitions of unity and check that you get the same thing. I'm not sure that it's so simple. And the second remarks, which is interesting. You remember we sometimes have a map, a smooth map between two manifolds. A smooth map not mat, a smooth map between smooth manifold. And you remember when we have a smooth map between manifolds, we can pull back a tensor field from one to the other one. So if phi is a tensor field on the final one, be careful, it's a pullback, so it goes into the other direction, then f star of phi is a tensor field on M. And you can wonder, oh, I'm able to do integrals on both. What is the relation? You can wonder if you integrate now phi on N, and if you integrate f star phi on M, as long as precisely it's integrable, you can wonder, oh, do we get the same thing? And the answer, you cannot fix the sign by this, simply because you remember you have two orientations. And when we have defined f, it doesn't encode the information about the orientation. So if you change the orientation, you are going to get a minus sign. So it means either the two manifolds are oriented in the similar way and you get an equality, or if one is oriented in the different orientation because you have always this double choice, then you get a minus sign. So it doesn't mean you have the two things simultaneously. It means either one or the other one, depending on the choice of the orientation. And if you are very careful, probably you can control this. But so it's good. It means the theory is consistent because we have a way to transport or transfer a tensor field from this space to that space. The integral gives us the same thing, modulo sign.
Predict the sign?
If you are a genius, probably. I told you, if you are very careful about the orientation, probably you can control the sign. If you just give one orientation to both or on each manifold, probably you cannot control the sign a priori. You need to be a bit more clever. Okay, what's the use of these integrals? And now this is very important. Listen. We have seen in calculus 2, we have different theorem. Please, oh, you have your exam of calculus tomorrow. So probably midterm, probably you have seen or you will see something called divergence theorem, Green theorem, or Stokes theorems. What are these theorems? They often relate an integral of something to another integral of something on a space of a different dimension. If you think about Green's theorem, it's in 2 dimensions. You integrate something inside a domain, and it's equal to another quantity outside. The divergence theorem is quite similar, and Stokes' theorem is also of this type. Okay. I'm claiming, and this is one report, I'm claiming that they're all encoded in one statement, theorem. And we are going to use everything. This is called Stokes theorem. And what I would be happy is that 1 or 2 or 3 students try to take this general framework, this general statement, and deduce the theorem we have seen in calculus 2 about divergence, Green theorem, and Stokes theorem. They are encoded in this. There is a small work to extract them. So let me precise. Let M be an oriented manifold. So I need an oriented manifold with boundary. Because if there is no boundary, one term is going to be 0. And the boundary is denoted by this. And the boundary is endowed with the induced orientation. I mentioned just before that whenever you have one orientation on the manifold, there is a canonical orientation on the boundary. There are formulas how to deduce the orientation on the boundary. Now, it's the first time I use this letter iota from, I like it. It's an I without a dot. It's called iota. Iota, I remember last week I mentioned the boundaries itself. Where is my, oh, yes, it's here. I mentioned last week, you have a manifold. This is a manifold, it has a boundary. So the boundary is itself, if the manifold is of dimension M, the boundary, I hope nobody takes a picture. The boundary itself is of dimension, no, M minus 1. Of course, I know. Okay, so you can look at the map. We just fix the boundary as the boundary of this manifold, of the big manifold, because you can separate the boundary and consider it just as a manifold of dimension M minus 1. Iota is what we call the inclusion map. You just say, okay, the boundary is really the boundary of this manifold. Now I take M form because I only know how to integrate M form. So I'm taking M-1 form on M. Sorry, I said something wrong. I'm taking a M-1 form on the manifold, and I don't know. I can take it with compact support if I'm scared about the integral, but I'm not scared. Then what are the objects I want to consider? Iota star. Iota star is from the vector field on M to the vector field on the other one. So iota star takes a vector field on M to a vector field on the boundary. Can you please stop talking, you two? And what is Stokes' theorem? Stokes' theorem is that the integral of iota star of phi is equal to the integral V. So please check first that it is meaningful. No, you wait. You first check that it is meaningful. I think it is meaningful because look, this is of dimension, it's a vector, it's a tensor field of dimension M-1. We integrate on a manifold of dimension M-1. This is exactly what we have seen before. And the right-hand side is the exterior derivative. The exterior derivative on a tensor field of degree M-1 altogether, it belongs to, it increases the degree by 1. So it's for M form. And we can integrate this M form on a manifold of dimension M. This is Stokes' theorem. It relates the integral on the boundary of this M-1 form to a M form or M tensor field, or precisely M tensor field on the manifold itself. And now this D makes sense because if you remember Green's theorem or Stokes' theorem in calculus 2 or divergence theorem, you had some derivative always. This D is nothing but precisely taking care of this derivative. Yes?
Should be the inclusion map of the boundary rather than just the boundary.
This line or the following line? Yes.
Right. Delta and instead of delta, should it be I delta?
No. Whenever we have a function, I already used it 2 times today. When we have a function from one manifold to another one, the upper star take vector field on this one or tensor field on this one to tensor field on that one. So this is correct. No, please check your definition. And okay, you would be surprised, of course, the proof is not completely short, but it's not so difficult. It's essentially the same proof as we do in calculus. If you remember here, we decompose into small square, and then we add the contribution of all small square and so on. This was Green's theorem. The general proof is not so different, except that you have to understand a little bit better what is this. But if you do it in local chart, it's essentially what we do in calculus. But it contains all the theorem we have seen in calculus. So one exercise is from this, deduce what we have seen in calculus 2. So for your exam tomorrow, please deduce from this formula what you, no, but maybe it is in the second part of this, of your, no, it's the second part of the second semester. It's not in the first part. Yes? Because, Otherwise, phi, where would be I need to define something on the manifold in order to take the exterior derivative. So if I define phi on the manifold, I need a way to also say something about a function on the boundary. Or if you define it on the boundary, you need to put it back to the big space. So no, you need something like this. Okay. So it makes sense. There is one more thing that I need to define today about integrals. Is I have defined, so far we integrate so fast. We integrated. We have integrated M forms. Maybe what about F simple stupid function, smooth function on your manifold? Can you also define an integral of just a function on your manifold? And the first answer is no, because as I mentioned at the very beginning, we don't have a measure on the manifold which replaces the Lebesgue measure. So how do we do it? If we want to integrate this, precisely we need to use a M form. So we need, I just put a measure in this sense, but what is a measure here? It means M form. So I can give you the definition of the integral of F, but you will be disappointed. For integrating F on M, we need to fix M form, and then this is the only way we can do it. The integral of F on M is in fact the integral on F phi on M. Well, is it well defined to do this? The answer is yes, because you can always take an M form and multiply it by a C infinity function. This is still M form. And what is a property which is hidden here? We have seen the notion of C infinity module. I mentioned it once. I said C infinity of M module means you can multiply on the left by smooth function. So this is true. I don't want to emphasize it too much, but it's still true because this set of M forms is a C infinity of M module. It simply means you can multiply on the left. It's quite clear. What is this phi p? You evaluate at 1p more precisely. I just remind you one thing. What is f phi at p? It is f of p, which is just a number, times phi of p. No matter what is phi of p, here phi of p is a tensor. It's an M tensor. Then you can multiply it by a number. So it's not surprising that you can do this. What is a drawback is that if you change this phi, you get a different notion. But later on, we will see that quite often there is a canonical choice for phi. But yeah, this definition, so be careful, this definition depends on the choice of phi. But once it is fixed, it's meaningful to give this definition. And in particular, you can choose the function 1. In particular, if f is 1, we set the integral of 1, which is the integral of 1 phi. It has a name. It's called the volume of M. But of course, if I want to be correct, I have to indicate that it's once I have chosen a tensor field of M tensor field, M4, more precise. Of course, if at a certain point there is one canonical phi, then it makes this less dependent on the choice. All right, so we know how to integrate M forms. Yes.
Define phi, this M form, you have like A times A of root T and then the dx1.
Yeah, the wedge product.
But for this one, do we need the A of T to be 1 here for this particular phi?
No, no. I told you this definition depends on the choice of phi. And for now, I have no reason to take a special one, but because the definition is valid for anyone. But yeah, if later we have a specific one, and in some cases there is a specific one, we will choose this one. But up to here, there is no reason to choose a specific one. Okay, the next section is much shorter. It's about line integrals on manifolds. And again, this is it will remind you something we did on calculus. We didn't doing calculus 2. So let's see the parametric curve. Okay. So I use the second one today. We have some parametric curves on this umbrella. You can see this is a function taking value. Sorry, it's a function from AB taking values in a certain on M. So this is a parametric curve, and I call C, capital C, the image. So this is C of the closed interval AB. Be careful, this is a manifold with boundary. This is also a manifold with boundary. So we are dealing with manifold with boundary simply because at a certain point I need to evaluate C at A and C at B. If I take it open, I have a small problem. So yeah, I need to take with boundary. Or if you don't want to take with boundary, the most stupid thing is to take a slightly longer interval. You take AB and you take an open set B plus epsilon and A minus epsilon, and then it's going to be an open interval, and you can keep without boundary and still it's well defined on A and B. There is nothing complicated here. Now, if you have phi in lambda 1 of M, I'm going to set I want to define a line integral. A line integral should be of dimension 1. This is why I've chosen a 1 here. The integral of phi along C, this is capital. Okay, it's a capital C. Now it's a definition, the integral of C star phi from A to B. Is it well defined? Yes. Why? Because C is going from this manifold to this one. So the star is going from the function on M to the function on AB. It means this is nothing. In local coordinate, you would have f of it dt, since the C star phi is of the form f dt. It has a representation of this type. It's one-dimensional. So this line integral is again something that we shouldn't be surprised. And there are a few theorems or a few lemma, a few results which I want to state because they should remind you something of calculus, and they are not difficult to prove. If phi is now of degree 0, and remember degree 0 means just a infinite function with value in R. Oh, infinite function on the manifold. Then the integral of d phi on C, the exterior derivative of something of degree 0 is of degree 1, so it's well defined, is equal to phi at C of B minus phi at C of A, something which should be familiar to some of you. And integrate on some curve, depending on the properties of the function, it depends only on the value of the function at the boundary. If somebody wants to prove this, it's very similar to what we have done in calculus 1. And now I want to do something slightly different. I want to consider a family of curves which start at P, finish at Q, and they are smooth. And I can transform continuously one into the other one. So how can I describe these different paths from P to Q? I'm going to consider a function of two variables. H from 0, 1 times AB to M. And what is the first variable? The first variable is going to choose the 0 curve, let's say the 1/2 curve, 3/4 curves, and the 1 curve. It's just a parameterization of these different curves. This is this variable. So what we have with, so H of epsilon A is always a point P for any epsilon between 0 and 1, and H of epsilon B is always Q for any epsilon belonging to 0, 1. Ah, I should mention this is smooth. Sorry, the function H is smooth. Otherwise, I can have anything. And the other point is, now I want to compare the first curve on the last one. So I set C0 of t, which is going to be H of 0 t, and C1 of t, which is going to be the H1t for any t in AB. So what I'm just doing, it's a complicated way to say I'm considering a family of curves that can be smoothly transformed into the other one. Or each one can be transformed into another one. And then what is the theorem in this framework, which should remind you also something from calculus 2, is that in this framework, It's a theorem. In this framework. If you take a phi, which is one form on M, then the integral of phi on C0 is equal to the integral of phi on C1. Oh, no, but there is a condition. It's not true in general. If such that d phi is 0, then so what does it mean? It means that these integrals are independent of the chosen path. You could think that the second theorem is a consequence of this lemma, but be careful, it's not the case. It's not always the case. Why? Why it's not always the case? Some of these phi satisfying this are of the form. Okay, I should use a different letter. So let me keep these two things. So it's a remark. It's unfortunate that I have pi on both. So, remark. Let's see. If, okay, let me change the letter, otherwise I cannot make this remark. So let me change the letter. I take a field which I call psi, which is deep psi, and psi. It's unfortunate because this one is of degree 1 and this one was of degree 0. So okay, it was not a good notation. Now, if psi is something, it's an exterior derivative of a phi, then what we know, the exterior derivative of psi is of course 0. Then deep psi is d of phi, which is d square of phi, and we know that this is 0. So it means if you start with a psi which is of this form, then automatically it satisfies this condition. But they are not all of this form, and this is related to the Durham cohomology, but not all psi satisfying, not all psi satisfying deep psi is equal to 0 are of the form psi is a d of somebody. Some of them are, but not all of them. And precisely the Durham cohomology is a way to measure the difference of these two sets, the sets of those who are of this type and those who are not of this type. But nevertheless, this theorem or these two results are something we have seen in calculus 2 in a restricted framework. So it means they can be deduced from what we have here. So if somebody wants to prove these, it's most welcome, and it's not so difficult. Okay. And it's a way to practice these notations. And the last remark, everything is smooth in my setting. From the very beginning, I have smooth fields, I have smooth manifolds. You can observe that when I write these integrals, I don't need smoothness. Usually continuity is sufficient, or maybe one derivative. So don't think that smoothness is really required for this kind of thing. It's convenient because we have been dealing with smooth objects, but it's not a strong requirement. Okay, chapter 4 is finished. Do you have any question or remark? So if you think about it, we have seen today integrals of M forms, and it's quite natural because the formalism gives us everything for this. Then we can integrate also functions, smooth function on the manifold, but you need to choose a kind of reference, which is one M form. And then we have seen these line integrals and two results about line integrals, which are something quite familiar from calculus 2. Okay, we still have a few minutes. We can start the next chapter, except if you have some question. Heavy do, no question for now. Or maybe online. Online, if you have also some questions, of course you can interrupt me. Also, you're free to interrupt me. Kato-san, if you want to ask questions or say that I made a mistake, you can also interrupt me. Okay, Riemannian manifold. They appear at many places. This is chapter 5. Riemannian manifold. They are very useful because they are very close to Rn. And in fact, I already introduced them. So I just need to remind you what is the definition, because I already gave it. A Riemannian manifold is a smooth manifold. With a certain field. If I make it very short, it's this, which is positive definite. But of course, you have to remember what is the sigma 2 of M. Who remembers what is sigma 2 of M?
It's a symmetric tensor. Oh.
Not symmetric tensor. No, symmetric tensor field. Symmetric tensor field. Yes. Of two variables. So what is this phi? Phi indeed is a map from M to to tau 2 or sigma 2 of T of M. So this is a set of symmetric tensor on two copies of TPM, which is positive definite. But in fact, yes, symmetric tensor, which is positive definite, and a tensor is in this case, a bilinear map. But in fact, what is hidden here, and today I want to say it, we have matrices. So I'll make a remark. On Rm, I do it on Rm. What means positive definite? What means positive definite? Maybe I should recall it somewhere. It means phi p, and you put 2 times the same vector. This is always bigger or equal to 0, and you have equality with equal to 0 if and only if x is itself, xp is itself 0. This is the meaning of positive definite. It's positive and equal to 0 if and only if you have xp is equal to 0. So on Rm, any positive, so this is very concrete, any positive definite matrix, and I will use the letter capital A for matrix of size m times m. So if you take a matrix which is positive definite, and I will recall what it means also. I'm claiming that any positive definite matrix defines a bilinear map. A bilinear map on Rm. Rm. And how? More precisely, you take two copies of Rm. Inside, you take a vector x and a vector y. It's more natural in this setting to call it x and y. Goes to scalar product x, a, y. This is my notation for scalar product. Maybe you prefer x dot ay. What means you prefer something else? Okay, but no matter this is a real number, why is it linear? Because check, it's linear in y if you take y1 plus y2 or plus lambda y2, it's linear in this argument. The same, it's linear in this argument, everything is real. So it's a bilinear map, and so it's bilinear. And by definition, x, ax is bigger or equal to 0 because I chose a matrix which is positive definite. It's exactly this meaning with equal to 0 if and only if x is 0. Why I emphasize this? Because it means whenever I'm thinking about Riemannian manifold, so whenever I'm thinking about for every p, we have a bilinear map on this, you can identify this vector space with Rm. So it means, in fact, at every p, you have a matrix, a positive definite matrix which defines a bilinear map. So this is a way of thinking about Riemannian manifold. Thus, I just write what I just mentioned. Thus, we can think, even if it's, we can think of phi is as a map M, take a P, goes to a, write it like this. What does it mean? I just keep the structure of a matrix which depends on P. You can enter a vector here, you can enter a vector here. It's going to be bilinear and definite positive with AP belonging to M of R, positive definite. Why it's not the best way to think about it? I mean, it's correct, but when you write a matrix, it means you have chosen a basis, you have done some choices, while with this notation, you don't need to choose a basis, or you don't need any specific choice. But still, if you want to keep in mind, a Riemannian matrix, a Riemannian manifold is a manifold with a function which at every p associated definite positive definite matrix. It's not wrong, but you have done some specific choices for this. Do you have any question about the definition of a Riemannian manifold? Now you can wonder, does it exist? Yes, Rm is certainly one, but do we have other? For example, my favorite bone or my umbrella, is this a Riemannian manifold?
It's also polymorphic to Rm.
What means holomorphic to Rm? We haven't introduced this. So it turns out that yes, there are plenty of Riemannian manifold, as we can see still within 1 or 2 minutes. So first, I want to transfer, this is an easy lemma. I want to transfer the structure of a Riemannian manifold. Oh, by the way, I didn't mention, but phi is called a Riemannian metric. So when you have a Riemannian manifold, it means you have a Riemannian metric. So now let F be a map between two manifolds, a smooth map between smooth manifold. You can wonder if one of them is endowed with a Riemannian metric. Can you put a Riemannian metric on the other one? And I need a little bit more than just a smooth map. Let F be a smooth map between smooth manifold, which is an immersion of M into N. Yeah, we spoke about this a long time ago, but how you should think about it. Immersion is, you need to write the Jacobian. When you take chart, you need to write the Jacobian. And the Jacobian should be of the rank of this one. This is immersion, which means you don't, in this map, you don't lose really any information on M. So in a sense, N is of bigger dimension. This map transfer M into something of bigger dimension. There is a precise definition, but essentially it means like the curve when you take an interval and send it as a curve on an interval, typically this is the immersion. You keep the information of the initial manifold. So then if N possesses a Riemannian metric, phi, then the pullback, it's always the same. We have to come back for tensor field. We have to come to bring back from N to M. Then this pullback is Riemannian. Is a Riemannian metric on M. And this is not so difficult because you can check. We already know that a symmetric tensor field is going to be pushed to a symmetric tensor field. What you need to preserve is this positive definite condition. But if you think about this positive definite condition, it's not difficult to bring it to the other manifold. So this is not a surprising lemma. There is nothing very complicated. You just need to write what it means. Now, I will finish with the next statement. This lemma plus the notion of partition of unity implies the following theorem, which I was a little bit surprised when I saw it for the first time. Any smooth manifold can be endowed with a Riemannian metric. So it means take any smooth manifold, you can always find one Riemannian metric, so one symmetric two-tensor field, which is positive definite. Can you a little bit guess what would be the proof? With the two ingredients, I mentioned this lemma plus partition of unity. Try to guess how we would start a proof. No, no, no. Is it written Stokes theorem here? No. Stokes theorem is a relation between manifolds and its boundary. It cannot appear here. No. Remember, manifold, locally you have charts. This is a U, this is a phi. This is part of Rm. We have matrices, we have positive definite matrix. So it means we have symmetric tensor field here. Locally, I can bring them back here because of this lemma. It means locally, I construct a Riemannian structure on this. And now, remember, we can cover our manifold with an atlas. We can find a partition of unity which is subordinate to this atlas. So it means you construct locally a Riemannian metric, and then you put the different parts together. It's not a proof. Of course, you have to be careful, but this is the idea. You take always remember, a smooth manifold is locally not very different from Rm. So you can take part of the structure from Rm, bring it back to the manifold, and now we have this notion of partition of unity. So we decompose the space here with this partition of unity. So with a family of functions summing up to 1. Remember this trick, we add a 1 somewhere and we decompose it. It's not a proof. I don't remember if I put it as an exercise, but if you think about it, it's not completely surprising that any smooth manifold can be put with a Riemannian metric. So it means Riemannian manifolds are quite common. Okay, I will stop here. What is the next step with Riemannian metric? We can now define the length of a path. We will do this next time. I can define what the distance on the manifold. Oh, maybe I can do it here. We will see that with this Riemannian structure, we are on the manifold. We take 2 points. Of course, we can construct plenty of paths. We can measure all of them, what is the length of all these paths. And then I will take the infimum, and the infimum will be the distance between 1 point here and 1 point here. So on a Riemann manifold, thanks to this Riemannian metric, we can define lengths and we can also define angles. So the next step is precisely to work on this. Okay. That's all for today. If you have any question, you can ask me at any time. Don't forget reports. Yeah, especially if you are third and fourth year, I'm really expecting that you submit on a regular basis. If you are second year, you should still submit something. And first year, it's really high time as well.